Monte Carlo Integration, Fall 2012, Marshall Tao.
Seth Montgomery.
Amber Rush Jones.
Today we'll be exploring the idea of Monte Carlo integration. What is Monte Carlo integration, you may ask? Well, first, we need to discuss the concept of Monte Carlo mathematical methods. A Monte Carlo method is one that uses random sampling to form a mathematical approximation. As the sampling increases, the approximation becomes more accurate. The method was formally created and improved by John von Neumann and Stanislaw Ulam while creating simulations for an atomic bomb for the Manhattan Project. Neumann coined the term Monte Carlo after the city of Monte Carlo in Monaco. Ulam's uncle would go to the city of Monte Carlo to gamble, and the term seemed fitting because of the degree of chance and probability that went into the method.
However, this wasn't the first time in history that the ideas of Monte Carlo integration were used. In the Buffin's needle experiment, the principles of the Monte Carlo method were used to estimate the value of pi. A series of needles were dropped on the floor made up of flat, parallel strips of wood.
In 1946, Stanislaw Ulam was doing research and came across a problem he could not solve using conventional, deterministic mathematical methods. He then looked into the idea of using random methods when working on his experiments. One day, Ulam was playing a game of solitaire when he began to question the chances of 52 cards being laid out in perfect sequential order. After trying and failing to find mathematical calculations to predict the behavior, he started to simply lay out the cards and count the number of successes against failed attempts.
Soon after, Ulam and Neumann began working together on the Manhattan Project. Together, they were able to expound on Ulam's ideas and create Monte Carlo integration the way we see it today.
Besides simply creating an easy method for calculating complex integrals, the work of Ulam and Neumann has much greater benefits. Because of the need for randomness in Monte Carlo calculations, the use of computers to randomly compute numbers greatly increased, and computers began to be used more in math.
Here's an example. One way to estimate the area of a pond in a field is to throw stones so that they lie randomly within the boundary of the field. Then, you would count the number of times a stone lands in the pond. The area of the pond is approximately the area of the field multiplied by the fraction of stones that landed in the pond. This simple procedure is an example of the Monte Carlo method. As you can see here by this computer simulation, random points are being generated along the curve of sine x over x. Oops, let's get rid of this thing here. The fraction of points underneath the curve to total points multiplied by the area of the window with the curve will give the approximate area. As you can see on the right side, as the number of points increases, the estimated area grows closer and closer to the target value.
The Monte Carlo method applies the principles of the mean value theorem to approximate integrals. In the mean value theorem, if f of x is continuous over an interval from a to b, then there exists a number c between a and b. And if you multiply the length of the function, or b minus a, by the average y value of the function, then you'll get the area of the function from a to b. As you can see in this picture, the height of that horizontal line is the average value of the function. And if you multiply the length from a to b times the height of that horizontal line, you will get the same area as the area under the curve.
While the mean value theorem states that there is a value c, which is the average y value, which can be multiplied by the interval to find the area under a curve, it does not give us a way to help obtain the value of c. The Monte Carlo method is so useful because it can help us obtain the average y value by multiplying the ratio of dots under the curve to total dots by the maximum height of the interval. Because of these principles, you don't have to know the formula of a curve to find its area.
The mean value theorem uses the average y value of a function and multiplies it by the length of the interval, which will account for the area under the curve, while the Monte Carlo method plots random numbers on the interval and uses the fraction of the number of points inside the curve over the points outside the curve and multiplies it by the area of the interval. Now let's work an example. On this function, the x value of a is 1, the x value of b is 10, and the maximum y value is 4. So we ran a Monte Carlo integration and found that 88 of the points were located under the curve and 12 were located above the curve. So to find the average y value, which is c, you take the number of dots under the curve and you put that over the total amount of dots and multiply by the y value, the maximum y value, which is 88 over 100 times 4, which will equal 3.52. Now that we know the c value by using the Monte Carlo method, we can use that value for the mean value theorem to find the area. To do this, you take the c value, which is 3.52, and multiply it by b minus a, which is 9. So the total area under the curve is 3.52 times 9, which is 31.68.
Okay, let's work through another example. So I'm going to draw a graph of this function. And we'll take the integral from a equals 2 to b equals 5. And the maximum y value is going to be 10. Now let's say we run a Monte Carlo integration technique and we take a bunch of random dots and we do it 100 times. And at the end of it we find that 66 times 66 of the dots were underneath the curve, which means that 34 of the dots were outside of the curve. So 66 were in and 34 were out. So because of this, we have 66% of the dots were inside. Now we take 66% and we multiply it times the maximum y value. In this case, it would be 0.66 times 10. This gives us 6.6. I'm going to guess 6.6 to be about right here. And that gives us the average y value of this function, which given by the mean value theorem is c. So I'll put c here. Now we take the interval, which is b minus a, or the length of the interval, b minus a equals 5 minus 2, which equals 3, and we multiply that times the c value, which is 6.6. So we have 3 times 6.6, which is 19.8. So using only 100 dots in the Monte Carlo integration, we estimate that the area underneath this curve from 2 to 5 is 19.8.
Okay, we're going to do one more example just to be sure. So I've got my graph here, and if we just have a random function, it goes up like that. We have our a value here, which is 2, and our b value here, which is 7. And we're going to have a maximum y value there, which is going to be 10. And if we do the Monte Carlo method and we plot 1,000 random points all over here, we find that 558 of them are going to be under the curve. And 442 will be over the curve. So if I have a calculator, we find that 558 over 1,000, which is 0.558, which is our C value. So if we take our Y value, which is 10, multiply by 0.558, we're going to get 5.58, which is our average y value, which should be about right there, which is C. So if we want to use the mean value theorem, then we C times B minus A, which is our intervals, which will equals 5.58 times 7 minus 2, which will give us approximately 27.9, which is the area under that function.
Monte Carlo methods have a wide number of uses in our world today. In biology and biochemistry, Monte Carlo simulations have been used to model molecular activity and the interactions between molecules. In the geophysical world, Monte Carlo analysis has been used to predict the stability of geological slopes. In marine engineering, Monte Carlo simulations have been developed to create probabilistic scenarios when assessing damages to ships. Monte Carlo methods are also used to model weather systems, estimate the prevention of diabetes and other diseases, and to create models used for financial planning.